Welcome back to the lab. Welcome back to EEforEveryone. Man, it feels good to be set up again and making some more videos. Heck yeah. We've got a really exciting video for you today. Today we're going to be picking up our series that we're calling What Even Is, where we've been talking about current sources, this fundamental component, the current source. And today we're going to do a little bit of improvement. Where we left off in our last video, we were doing some stuff with a BJT current source. I think that's where we left off. And now we're going to be amping that up by moving into an OpAmp. We're going to be using an OpAmp to improve the regulation performance. Hopefully this will have a little bit less error. Hopefully this will have a fewer temperature effects. Hopefully it will be a better design. Okay, that's enough talking. Let's dive in. Okay, there's a few different things that we could do to build this current source, but what I want to focus on is something that's a little bit easier. So there's a high side pass element or a low side pass element, and basically what that means is we've got a choice to make. There's some voltage source in this design somewhere, and we either need to put our regulator here or we put it here. And then here's our load. That's what we're talking about. Okay, so if we're going to power our load, do we want our current source to be here or here? Well, let's talk about some things about what that decision really means. So we're going to call this one high side versus low side. Okay, pretty simple. And the reason why one is called high side and one is called low side is simply because one is closer to ground and one is closer to V+. It's really quite simple. Okay, what does this mean? Well, typically, I would prefer a high side regulator. You might be thinking to yourself, why? That sounds pretty complex. We need to do current sensing up here. We need to do all kinds of stuff up there. That seems kind of complex. And, well, let's say this were 100 volts, 200 volts. That can be kind of complex when you've got this control loop kind of touching something that's at a few hundred volts DC. So there's some complexity with needing to add this DC offset to a bunch of control circuits. However, the low side isn't without its complexities as well. Having the low side of your load tied very close to ground is usually a good thing, right? This is usually interfacing with other circuits, and you need to have a common reference. So if you're using a low side regulator, that means that your load could be hanging off at, I don't know, 100 volts, 50 volts, 25 volts, and for a lot of circuits, that much DC offset could be a problem. It's just something that I think about, something to keep you up at night. We are going to be going for a low side regulator in this series. We're going to be basically adding a dynamic impedance on that low side that will enable our load to see a constant current. So for something like a string of LEDs, for something like, let's say you want to do speed control of a motor, or no, torque control of a motor instead of speed control, you could apply a constant current instead of a constant voltage, and that motor or that string of LEDs wouldn't really care if the low side of the motor were 10 volts off of reference, but just keep in mind this might not work for all applications. That's kind of the fundamental principle of what we are doing here today. So let's dive in a little deeper. Let's sketch out the schematic that we're going to be building. Well, we're going to need a critical component. You might have guessed, this is an OpAmp, an operational amplifier, and we're going to be designing ours to do, it's going to need a bipolar supply. And we'll use 10 volts, 15 volts, something like that, to supply this OpAmp. There's going to be the gate of a MOSFET, which has an internal body diode. I don't really like to draw it like that. It's got the internal body diode. And we're going to have a little current shunt resistor. And that comes on back. Now, this is where The op-amp behaves kind of like a comparator, which is what we were talking about in our previous series. Yeah, check out the comparator series if you haven't seen it. It's pretty great stuff. A lot of people liked it. I personally think it was okay. So definitely high vote of confidence there. Check out that playlist. So this is kind of like the same thing as a comparator, where it's always trying to make the inputs equal. It's trying to modulate the output to make the inputs equal. And so we need to make sure that we set this in the correct configuration, because if we don't, it's going to go twing like a comparator and not linearly regulate output current. Okay, so as the output voltage goes up, the current through RS will go up, and the voltage across it will go up. So these are directly correlated. Increases in voltage will increase the current. Okay. And this op-amp will increase the output voltage whenever the negative terminal is less than the positive terminal. So if the negative terminal is greater than the positive terminal, it will turn the output voltage down. And to the converse. Converse, is that right? I don't know. So basically what I'm trying to say is we need to hook up this sense line to the negative input. And then we have a VREF, a voltage reference, that ends up setting our current set point. And it's as simple as that. So we've got our low side pass element, our low side shunt resistor. Now, if current's really high, you might need to do a Kelvin connection here, where you take these two voltages and sample them with respect to each other, not necessarily to an assumed ground reference, but we'll talk more about that later. But yeah, so that's the fundamental configuration. That's really all we need to use an op-amp to regulate current. So how do we connect this to our load? Obviously, there's no voltage source baked into this. It's more of a sink than a source, if I'm being honest. So that means we need a voltage source somewhere. And just like last time, this could be unregulated, this could be regulated, but we've got some form of source that's applying a voltage. And now, depending on what you want to do, you can make this pretty sneaky. You can make it a little more efficient, because this is linear, right? This linear regulation stage is going to be kind of lossy. But if you want to be a little tricky and you want to build a current source that has pretty good efficiency, you could make this voltage source kind of chase your load. So you could set that set point to like 10 volts above whatever you're regulating to give you a little bit of room for transient response or dynamic load situations. But you can design it such that you're not burning 100 volts in your MOSFET when you don't need to be. Hopefully that made sense. So you need this voltage source, and then your load just connects right there. And just like last time, just like last week or a few days ago, when we were talking about current sources, a resistive load is just about the best. It's just about the most simple, straightforward load you could ever have. That is, it's not very difficult to regulate current through a resistive load, so we're going to add a little voltage source to do some dynamic load transients. So this is our basic op-amp circuit. This is the fundamental, the simplest way that I think that we can build a circuit that will attempt to regulate current with an op-amp. This is where we're going to start today. So let's switch over to LT-Spice and see what this circuit can do for us. Let's find some things that are working well. Let's find some areas that leave some room for improvement, and let's talk through what we might want to change. Okay, let's dive in. And look at that. We are in LT-Spice with a circuit drawn. Before we get a little too crazy. There we go. Before we get a little too crazy, I just want to take a moment to highlight some of the important features of this design. So, what do we have? We have that voltage source we were talking about. We have the voltage input, this bipolar positive negative input that is feeding, well, it's not feeding our op amp right now. We're just doing single-sided because I want to show you the difference and why we need that. Then we've got two voltage sources that we can use. There's one that's like a dynamic triangular slewing thing, and there's just this constant voltage reference. You can see we've got our shunt resistor, we've got that pass element, and we have our load configured to make some dynamic transients. In this case, we're not modulating our input at all. We're just leaving that the way that it is. Now, I guess let's hit run. Let's look at what I've prepared for you. So allowing the simulation to run. Let's just give it a check. It looks pretty good, right? So this is a 25 milliohm shunt resistor that we've selected, and with 0.25 volts as our reference, that means we should be regulating to where this node is about 0.2. That's 0.27. That's not right. Wonder why. For those that are familiar with control theory, you'll know exactly why. The reason why that's not exactly correct is because we don't have a compensator. We don't have an integral term. We basically have, we don't even have proportional control. We don't really have control at all. We're just, yeah. We're just telling it to shoot for 0.25 and whatever happens, happens. Oh, that's fantastic. But yeah, so here you can see there's 250 millivolts. There is this error, 22 millivolts of error. But, I mean, in general, right, as far as 10 amps go, it's pretty good. That's pretty good. We're at 10.86 amps. That is, what is that? Percent error, 0.86 divided by 10. That's 8% error within 10%. It's not half bad. I think we can do a lot better with a very similar circuit, but as a starting point, compared to what our BJT was accomplishing, that is not half bad. Especially because, if you remember last week, the load, the operating point, the bias point, really, really affected the current regulation. And in this case, look at the voltage across our load. The voltage across our load is varying from 10 volts to 110 volts, but the current waveform is almost constant. That's pretty cool. That's working really well. Yeah. And why is that? Well, if we look, our gate, the gate of our MOSFET, there are some little dips. There's some little changes. Our OpAmp is doing some tweakage, for lack of a better word. It's sitting there and doing its best to keep the current constant. And you'll notice those little transients are in alignment with those load steps. Sweet. So, a couple things to note. I suppose that covers one of the things I want to make sure we talk about, the dynamic regulation. That was with a constant load. One of the first things I'd like to do to make this more aggressive is simply changing our reference from 0 amps to 10 amps, which is 250 millivolts, at a time of 2 seconds. And hopefully what we see is, hey, look at that. Even though our load is pulsing and going all over the place, we can see that when our current input commands turn on, the output looks pretty good. It looks like there's a little bit of overshoot. It looks like it comes up pretty fast. Let's see if I can zoom in on that time scale. What's interesting to me is how we settle out into this steady state error condition. You know, I almost wish there was some way that we could add something to this circuit that would compensate for that difference and really drive the error to 0. Stay tuned for our next video, because that's exactly what we're going to do. In the meantime, I want to expose a few other flaws of this circuit. though the transient response admittedly looks quite good, given that it's just a simple op-amp, a very simple compensation network. It's just an op-amp. Okay, so let's say, for example, we really wanted the circuit to work. The power dissipation in our downstream resistor is kind of a lot. 3 watts is kind of a lot. And if we put in a 10 milliohm resistor, like you do, and we change our current set point. So now Vref is up at 100 millivolts. Our resistor is 10 milliohms. So we would expect the same current. We would expect to see 10 amps, but we're seeing 13 and a half. So now our regulation isn't looking so good. Why? Well, because there's some amount of voltage. There's some amount of difference. We need an output voltage on V gate. And in order for the output voltage on V gate to be 4 volts, that means that there needs to be some difference on the input to really drive that. And in this case, that difference that makes 4 volts come out is 36 millivolts. And that's the steady state error that we're seeing. That's how much input we need to bias this MOSFET at this voltage. It's not really great. It's not really how I would want to see this thing work, and that's just dependent on the gain of that op-amp. So maybe there's something we can do to improve this a little bit, or a lot of it. So we've got this issue as the input voltage becomes smaller and smaller. There's an error term intrinsic to this op-amp where we need to put some voltage across it in order to make an output happen. And let's see what happens as we try to drive the output current even lower. And we're going to do that by swapping out our voltage source. What are we asking for? We are asking for 10 amps. That ain't right. We're asking for 25 amps with our 10 milliohm reference, and then down to 0.1 amps. That is a pretty small current that we're trying to regulate to. Can we do it? What are we seeing on the output? Ooh, yeah, we can see that steady state error really ramp up as we get low. Even though we're asking for 0.1 amps, we're getting 5. But on the high end of that, we're asking for 25, and we're getting, what is that? Where's my, oh, there it is on the other monitor. We're asking for 25, and we're getting 27. It's really not that good. And that's kind of what I wanted to highlight today. As we're getting down towards this low end, this is where having that bipolar supply really starts to become important. Because as we're trying to drive the FET closer and closer to 0, the V out low starts to be an issue where we start to hit the lowest voltage that gate can get to. And since we're in the linear region of the FET, maybe we're just not getting a low enough output voltage to really accomplish that. And you can see just by adding that bipolar supply, just by opening up the MOSFET to go negative if it needs to, we can now drive much, much closer to what is demanded. Getting down to that low end, what are we seeing? We're seeing, look at that, 109 milliamps. That's actually pretty good. That's actually pretty darn good. Look at that. But of course, that doesn't help our accuracy up at the 25 amp threshold. No, that actually helps quite a lot. Dang, bipolar supply, do it. But at any rate, there's still a lot to be desired in this design. To summarize what we talked about today, what do we have? We have a dynamic load that is chasing around this set point that we have defined. And it's regulating a current profile that is in alignment with the analog input, where 0.1 volts equals 10 amps because of our 10 milliohm shunt resistor. We have it configured this way, though it certainly is not ideal. We can see that we dissipate about 6 watts in that current shunt. When we're regulating, we're dissipating anywhere between 2 kilowatts and 4 kilowatts in this MOSFET. Yikes, to maintain a relatively constant load across that resistor. So pretty fun stuff. Pretty fun stuff. In this case, it's not a constant load because we're changing the load. But you can see that even though the voltage across the load is changing, the power is held constant when we want it to be. So that's kind of what we're doing. We've got a low side current regulator circuit. This one is built with a OpAmp, just a simple OpAmp. Stay tuned for our next video where we are going to be improving this design. We are going to be improving this design by adding some steady state error compensation. It's going to be fantastic. We're going to be compensating this with an integrator. We're going to be adding a OpAmp integrator and a error amplifier to build this up. So we're going to talk about difference amplifiers, and we're going to be talking about discrete integrators and how we can use that to improve this design. I can't wait. If you like this video, don't forget to hit that like button, get subscribed, or check out our Patreon page if you'd like to support us directly. For those that have decided to back us on Patreon, I really appreciate you. It helps us out a lot. It helps to keep this all possible. Thank you. Most of all, I hope that you learned something great today. I hope you enjoyed, and I hope to see you again soon. So thanks for watching EE for Everyone, and thank you for staying till the end. Bye.